rockets to how airplanes, well, which weigh tons, can lift off into the sky, or how you can push liquid through a syringe using just your fingers. Even something as simple as drinking from a straw. It's all about how fluids move and react to forces.
I'm nice, Malayno.
Usain Bataw.
I'm your one and only, Kate Manubi. And here with us is Leia Adolfo.
I'm Hannah Anet.
But before we proceed, we have our own learning objectives too. At the end of this self-learning kit, the students should be able to analyze fluids in various systems using Pascal's principle, understand the concept of buoyancy and Archimedes' principle, define Bernoulli's principle and the continuity equation. In skills, solve problems involving fluid mechanics, particularly Pascal's, Archimedes, and Bernoulli's principles. And lastly, in attitude, apply Bernoulli's principle and the continuity equation to relate pressure, elevation, speed, and flux in different fluid systems. So let's start by understanding what a fluid really is.
Fluids are substances that can flow, meaning their particles can move past each other easily. These include liquid, gases, and even plasma.
Even blood counts as a fluid? I thought that was biology.
That's commonly stated. In medicine, the blood is treated as fluid because it flows and follows the same physical law, like pressure and viscosity.
That field of science is called fluid mechanics, the study of how liquids and gases behave, whether they're moving or standing still. It doesn't just apply to water or air, it also includes fluids like blood, lava, and even honey. Many people think fluid mechanics is all about complicated math, but as Sir Neil Mars said, it's only complex if you make it complex. It's really about how fluids behave in the real world, and that's something we can all see every day.
According to Blaise Pascal 1653, when pressure is applied to a combined fluid, it spreads equally in all directions. That's why in hydraulic lifts, like the ones used in car shops, a small force on the one side can lift something heavy on the other.
In this example, we'll see how Pascal's principle applies to a car's braking system. A force of 100 newtons is applied to the brake pedal, producing a force of 500 newtons on the master cylinder. The pressure in the master cylinder is then transmitted through a fluid to 4 slave cylinders. The master cylinder's diameter is 0.5 centimeters, while each slave cylinder's diameter is 2.5 centimeters. The goal is to find the force produced by each slave cylinder. For our strategy, the force on the master cylinder, F sub 1, is 500 newtons. We need to determine F sub 2, the force on each slave cylinder. First, we calculate the areas of both cylinders, A sub 1 and A sub 2, using their diameters. Then, we apply Pascal's principle, which states that pressure applied to a confined fluid is transmitted equally in all directions. This is expressed as F sub 1 over A sub 1 equals F sub 2 over A sub 2. Rearranging for F sub 2 gives F sub 2 equals A sub 2 times F sub 1 divided by A sub 1. We replace the area with pi r squared since pi appears on both sides, so it cancels out. We only need to use the radii. The radius of the slave cylinder is 1.25 centimeters, and the radius of the master cylinder is 0.25 centimeters. Substituting into the equation, F sub 2 equals 1.25 squared times 500 divided by 0.25 squared. That's 1.5625 times 500 over 0.0625, which gives a result of 12,500 newtons. Therefore, each slave cylinder produces a force of 12,500 newtons. With 4 slave cylinders in total, the combined force equals 50,000 newtons. This proves how a small input force on the master cylinder can be multiplied by many times in a hydraulic system, exactly as explained by Pascal's principle.
Now let's move on to Archimedes' principle, which explains why things float or sink. It states that an object submerged in a fluid experiences an upward buoyant force equal to the weight of the fluid it displaces.
On this slide, we see the formula F sub B equals W sub FL. This means the buoyant force, where F sub B is equal to the weight of the fluid displaced by the object. This comes from Archimedes' principle. It says that any object placed in a fluid, whether fully or partly submerged, experiences an upward force equal to the weight of the fluid it pushes aside. We call that upward push the buoyant force. Next, buoyancy is something we experience all the time. When we get into water, we feel lighter. That's because water pushes upward on us. If an object is less dense than a fluid, it floats. That's why a human body floats in water and a helium balloon floats in air. The buoyant force is defined as the net upward force exerted by a fluid on an object. This happens because pressure is stronger at the bottom than at the top of the object, and that difference pushes it upward. If the buoyant force is greater than the object's weight, it floats. If less, it sinks. If equal, it stays suspended. You can also see the formula. F sub B equals F sub 2 minus F sub 1, meaning the upward pressure minus the downward pressure. Here, we can see two main forces, the buoyant force going up and the object's weight going down. If F sub B is greater than the W object, it rises. If F sub B is less than W object, it sinks. And again, Archimedes' principle tells us that the buoyant force is equals to the weight of the fluid displaced by the object. In this diagram, if you remove the object, the space it occupied is replaced by water with the same weight. That weight, the fluid's weight, is equal to the buoyant force. This is why we can use Archimedes' principle to measure the volume or density of irregularly shaped objects, for example, a rock or a piece of metal. Space an object occupies is filled by the fluid around it. The weight of the displaced fluid is what creates the buoyant force. Archimedes, the great mathematician and inventor, discovered this principle over 2,000 years ago, long before scientists fully understood what force even meant. It truly shows his genius and how far ahead he was for his time. Now, let's apply what we have learned in a simple example. We'll calculate the buoyant force on 10,000 metric tons of solid steel completely submerged in water and compare it with its weight. Then, we will find how big that buoyant force can become if the same steel is shaped like a boat, one that can displace 100,000 cubic meters of water. For the first part, we need to find the weight of the water displaced by the steel. Since the steel block is fully submerged, its own volume is equal to the volume of the displaced water. We can find that using the formula for density. Mass equals density times volume. In rearranging, volume equals mass divided by density. We take the mass of the steel, which is 1 times 10 to the 7 kilograms, and divide it by the density of steel, 7.8 times 10 to the 3rd kilograms per cubic meter. That gives a volume of about 1.28 times 10 to the 3rd cubic meters. This also means the steel displaces 1.28 times 10 to the 3rd cubic meters of water. So, the buoyant force equals the weight of that much water. Now, for part B, here, the steel is shaped like a boat that can displace 1.28 times 10 to the 3rd cubic meters of water. The buoyant force is the weight of this displaced water. So, we substitute the values. The density of water 1000 kilograms per cubic meter multiplied by the displaced volume 1.28 times 10 to the 3rd. When we multiply, the cubic meters cancel out, leaving kilograms. And that gives a mass of 1.28 times 10 to the 6 kilograms. In the next aspect, we multiply this mass by gravity, 9.8 meters per second square. That gives a buoyant force of about 1.3 times 10 to the 7th newtons. What we did there is multiply the density, mole volume, and gravity, canceling the cubic meter units, leaving newtons, which measure force. This means the water can push upward with a very strong force, enough to support the heavy steel. That's why steel ships float, because their shape lets them displace enough water to balance their weight. Now, this slide explains how density affects floating. Whether something floats or sinks depends on how dense it is compared to the fluid. If it's less dense, it floats. If it's more dense, it sinks. The buoyant force always equals the weight of the displaced fluid. That's why a loaded ship sits deeper in the water. It's denser, so it has to push more water out of the way to balance its weight. Fraction submerged shows how much of an object is underwater. We find it by dividing the submerged volume by the total volume. Since the submerged part equals the displaced fluid's volume, we can compare densities instead. So, the fraction submerged equals the object's density divided by the fluid's density, showing how much of it stays underwater. Finally, we have the concept of specific gravity. Specific gravity is the ratio of an object's density to the density of water, but it has no unit. It's just a comparison number. If the specific gravity is less than 1, the object floats. If it's greater than 1, the object sinks. If it's exactly 1, the object stays suspended in the fluid. This is what scuba divers try to achieve so they can hover underwater without rising or sinking. Specific gravity is also used in real life. It helps measure the condition of fluids such as battery acid, radiator fluid, and even urine in medical tests.
The continuity equation explains how fluids move when the path changes size. It says A sub 1 V sub 1 is equal to A sub 2 V sub 2, meaning the product of area and velocity stays constant. When the pipe gets narrower, the fluid must speed up so the flow stays steady.
Continuity equation tells us that when a pipe becomes narrower, the fluid speeds up. You can see this when watering plants. If you partly cover the hose opening with your finger, the water sprays out faster. Here's an example. A horizontal pipe with an area of 25 square centimeters carries water at 3 meters per second. It connects to a smaller pipe with an area of 15 square centimeters. Using the continuity equation, A sub 1 V sub 1 is equals to A sub 2 V sub 2. We solve for the new velocity. 25 times 3 divided by 15 is equals to 5 meters per second. Bernoulli's principle states that in a steady flow, the pressure of a fluid decreases as its speed increases. In simpler terms, when a fluid moves faster, it pushes less on the sides, meaning the pressure becomes lower. The formula is given below. P is the static pressure of the fluid at a certain point. Rho is the fluid's density. G is the acceleration due to gravity. V is the velocity or the speed of the fluid. H is the height or elevation at that point. Bernoulli's equation is similar to the conservation of energy equation. This explains how airplanes fly. Lower pressure is caused by the increased speed of the air over the wing. Since the pressure is higher beneath the wing is pushed upwards. Airplane wings are shaped to make air move faster over the top of the wing. When air moves faster, the pressure of the air decreases, so the pressure on the top of the wing is less than the pressure on the bottom of the wing. The difference in pressure creates a force on the wing that lifts the wing up into the air. Now, let's focus on the top part of the slide. It says, water enters a house through a 2 centimeter pipe at a pressure of 4 times 10 to the 5th pascals and a speed of 1.5 meters per second. Then, it flows upward 5 meters to a smaller pipe on the second floor, which has a diameter of 1 centimeter. We'll use the continuity equation to find the flow speed in the bathroom pipe. This equation tells us that the amount of water entering must be equal to the amount coming out, meaning the flow rate stays constant. Before we start with the formula, let's look at the given section at the bottom of the slide. The diameter of the inlet pipe is 2 centimeters, and the diameter of the outlet pipe, the one in the bathroom, is 1 centimeter. The height difference between them is 5 meters. The pressure at the inlet is 4 times 10 to the 5th pascals. The flow speed at the inlet is 1.5 meters per second, and the density of water is 1,000 kilograms per cubic meter. Now, moving to the right side of the slide where it says flow speed, we'll use the continuity equation which states that the amount of water entering is equal to the amount leaving, meaning the flow rate stays constant. The formula shown is A sub 1 times V sub 1 is equals to A sub 2 times V sub 2. That means the area times the velocity at the inlet is equal to the area times the velocity at the outlet. we rearrange it to solve for the outlet speed, giving us V sub 2 equals A sub 1 times V sub 1 divided by A sub 2. Next, let's substitute the values. The inlet area is 3.14 times 10 to the negative 4 square meters. The outlet area is 7.85 times 10 to the negative 5 square meters. And the inlet speed is 1.5 meters per second. So, we multiply the inlet area by the inlet speed, then divide by the smaller outlet area. After cancelling out the units, we get the final answer of 6.0 meters per second. This means the water moves faster in the smaller pipe because the same amount of water passes through a narrower space, increasing its speed. Alright, now let's move on to the next part of the slide. Here, we're finding the volume flow rate. That's just how much water passes through the pipe every second. So, let's start at the top where it says the volume flow rate is given by. It means we'll multiply the area of the pipe by the speed of the water flowing through it. Looking at the first equation, you'll see we're using the area of the inlet pipe, which is 3.14 times 10 to the negative 4 square meters, and multiplying it by the inlet speed of 1.5 meters per second. When we do that, we get a result of 4.7 times 10 to the negative 4 cubic meters per second. Now, if we move to the next line, the one that says this is equal to, we repeat the same process for the outlet pipe. Just to conclude, we use the smaller area, 7.85 times 10 to the negative 5 square meters, and the faster speed, 6 meters per second. The result is still 4.7 times 10 to the negative 4 cubic meters per second. That means the flow rate stays the same. The same amount of water goes in and comes out each second. That's what we call it the continuity equation in action. Now let's go down to the next part. This time, we're solving for the pressure at the bottom of the pipe. We'll use Bernoulli's principle here. This principle tells us that when water flows faster or moves upward, its pressure goes down. To make things easier, we set the height of the inlet pipe to 0 and the height of the bathroom pipe to 5 meters. Then we plug in the values. The pressure at the inlet is 4.0 times 10 to the 5th pascals. The density of water is 1.0 times 10 to the 3rd kilograms per cubic meter. The inlet speed is 1.5 meters per second, and the outlet speed is 6 meters per second. After substituting and simplifying, we get the pressure at the bathroom pipe, which comes out to be 3.3 times 10 to the 5th pascals. So, what does this mean? As the water moves up and flows faster through the narrower pipe, its pressure drops. That's exactly what Bernoulli's principle shows. When speed increases and height goes up, pressure decreases. Bernoulli's principle in flight explains how birds and airplanes are able to fly. The main idea is that the secret behind flight lies under the wings. As air moves over the curved surface of a wing, also called an airfoil, the air traveling on top moves faster than the air below. According to Bernoulli's principle, faster moving air creates lower pressure, while slower moving air creates higher pressure. This difference in pressure produces what we call lift, an upward force that pushes the wing and therefore the plane or bird upward. You can see in the diagram that on top of the wing, there's greater airspeed but less pressure, while underneath, there's lower airspeed but greater pressure. So when air hits the bottom of the wing and bounces downward, the reaction pushes the wing upward. This is how airplanes take off and stay in the air. Next, let's move on to another example, the inverted umbrella. When the wind blows strongly on top of the umbrella, air molecules on top start moving faster, which lowers the air pressure there. Meanwhile, the air underneath the umbrella remains lower, meaning it has higher pressure. The pressure difference pushes upward on the underside of the umbrella, causing it to invert or flip inside out. Finally, let's look at another everyday example, the shower curtain. When you take a hot shower, the air inside the shower warms up and begins to move faster. As a result, the air pressure inside the shower decreases. Meanwhile, the cooler air outside the shower has higher pressure. This higher outside pressure pushes the shower curtain inward, making it stick to you while you're showering. Again, this happens because of Bernoulli's principle. Faster moving air means lower pressure, and the difference in pressure causes movement toward the low pressure area.
In theory, we treat fluids as ideal: no friction, no stickiness, no turbulence. But in real life, fluids have viscosity. That is internal friction. Some think viscosity means thickness, but it's actually about how resistant a fluid is to flow.
Fluid mechanics applies everywhere. Hydraulic system use Pascal's principle. Ships and submarines use Archimedes. Pipes and airplanes depends on continuity and Bernoulli.
Even our own circulatory system depends on fluid dynamics. That's how our heart pumps blood throughout the body.
So, let's have a recap. In Pascal's principle, pressure spreads equally in all directions throughout a fluid. This means that when pressure is applied at one point, it's transmitted equally to every part of the fluid and the walls of its container. In Archimedes' principle, buoyancy depends on density. In other words, an object submerged in a fluid experiences an upward force equal to the weight of the fluid it displaces. This is why some objects float while others sink. In continuity equation, flow rate stays the same. When fluid flows through a pipe, the amount of fluid passing each point per second remains constant, even if the pipe narrows or widens. In Bernoulli's principle, faster speed means lower pressure. As the speed of the fluid increases, its pressure decreases, a concept often seen in airplane wings, where air moving faster above the wing causes lift. And lastly, real fluids. Unlike ideal ones, real fluids have viscosity and friction. These cause resistance, energy loss, and slower motion, making real-life flow less perfect than the theories predict. That wraps up our discussion on Pascal's principle, Archimedes' principle, Bernoulli's principle, and the continuity equation, and also the difference between real and ideal fluids. Thank you so much for watching and learning with us. This is Group 6 signing off.